If you remember, in the previous video, I believe, or 2 videos ago, I mentioned that we were making an assumption that the redox reaction was occurring in an acidic solution. But I also mentioned that we could also make the assumption that the redox reaction was happening in a basic solution. So we're going to talk about that now. If we're making that assumption that the redox reaction is occurring in a base, and we're trying to balance that reaction with the assumption that it's occurring in a base, truthfully, the process for balancing that is almost exactly the same. The only difference is we're going to make an adjustment at the very end. So we're going to treat the balancing the exact same way we did up to this point. The only difference is if at the end of the balancing we have some H plus in our balanced equation, what we're going to do is we're going to add OH minus to both sides of the reaction in order to neutralize that H plus into water. So if that doesn't make sense, it should make more sense if we actually do an example here. So we have a redox reaction occurring. Again, it's fairly clear what the two half reactions are. It's not immediately clear which one is being oxidized and which one is being reduced, but it's at least clear how we can split them up. Because the manganese is not turning into iodide. It's fairly clear how we can separate them. So let's go ahead and balance these two individual half reactions. And notice here, this is in basic solution, but like I said, we're going to do everything exactly the same until the very end. When we get to the end, we will add OH minus if we have H plus in our balanced chemical equation, which we will. So in this first half reaction here, we don't have the iodines balanced, so we're going to go ahead and add 2 there to get the iodines to be balanced. No need to balance oxygen or hydrogen. The only thing that needs balancing is the charge. So we have 2 negatives on the left, 0 on the right. Again, when you're adding electrons to balance this, you're always just adding however many electrons you need to the higher side to get it to be as low as the lower one. So we are going to add 2 electrons to the right. So now both sides are negative 2. Similar thing here with the manganese. So the manganese is already balanced. The oxygens are not. So we'll add 2 waters to the right side. So now our manganese and oxygen are balanced, but by adding the water, we've now messed up the hydrogens. So we have to add 4 H plus to the left so that we have 4 hydrogens to go with the 4 hydrogens we had in our water. So now the masses are balanced. Now we need the charges to be balanced. Nothing on the right side is charged. So we have 0 on the right side of this half reaction. But we have 4 plus from the hydrogens and 1 minus from the permanganate. And so we have plus 3 total on the left side of this half reaction. So because we have 0 over here, plus 3 here, we need to add 3 electrons to the left side of this equation so that, again, we're just adding electrons so that the side with the higher charge is lowered down to the same level as the lower side. And you might have noticed already, but just in case you haven't, with these half reactions, we always have electrons on the product side for one of the half reactions and electrons on the reactant side for the other half reaction. That will always, always, always be the case because one of them is a reduction, one of them is an oxidation. One of them is losing electrons. That would be this one. It's giving up electrons, 2 of them specifically. And one of them is gaining electrons. That would be this one. You have electrons as a reactant. So there are always going to be electrons on one side and the other side. If you balance the two half reactions and both of them have electrons on the same side, you did something wrong. All right, so the next step here, now that we have the masses and the charges balanced in the two individual half reactions, we need to get the number of electrons being transferred to be the same. Because if this side is giving up 2 electrons and this side is gaining 3, well, that doesn't make any sense. Where'd that extra electron come from? So we need the number of electrons to be the same. And the smallest number where those can be the same is if we multiply the top one by 3 and the bottom one by 2, which will give us 6 electrons on both sides. All right, so this is going to be a big mess, but we're going to do it. So we have 6 electrons plus, and what I'm doing here is I'm just adding everything together. So 6 electrons, 8H plus 2MnO4 minus plus 6 iodides. So that's all the reactants. Goes to 3I2 plus 2MnO2 plus 4 waters plus 6 electrons. Whew, okay. So if we check and see what we can cancel out at this point, we can make those electrons go away. And actually, I'm going to go ahead and just erase those because I know I'm going to need that space. So those electrons go away. And if this were occurring in an acidic solution, I would stop here. I would say done, done and done. No need to worry about anything else. But we are doing this in a basic solution. And so to take that into account, again, after we do everything else exactly the same, we're going to see how many H pluses I have on one side. In this case, I have 8, which is quite a few, on the left side. And I'm going to add that same number of OH minuses to both sides. 8 OH minus on the left, 8 OH minus on the right. What this is going to do is the OH minus is going to neutralize the H plus to make 8 waters. So those are now gone, and I have 8 waters instead. So now I have to again look at the reaction and say, do I have anything on both sides that I can get rid of? And I do. I have 8 waters on the left, 4 waters on the right. So those 4 waters are going to cancel out 4 of these waters, not all of them, just 4 of them, so that I have 4 waters left. And so my final balanced chemical equation is going to be 4 waters plus 2 permanganates plus 6 iodides goes to 3I2 plus 2MnO2 plus 8OH minus. Yuck. So, it is definitely a longer, more complicated process to balance redox reactions than it is to balance just the plain old simple reactions that we saw in Gen Chem 1. That being said, it is still just a process. If you follow the process, if you follow the steps, you do what they say, you should end up with the correct answer at the end. One quick note here. You might notice how we started, before we did the switch to basic here, we had 4 waters on the left, 4 waters on the right, 8 H plus on the left, and we ended with essentially those flipped and replaced. So we ended with 4 waters on the left and 8 OH minus on the right. the first time I saw this, I thought, oh, that's kind of a nifty shortcut. If I'm switching to base, I can just swap those two and replace OH minus with H plus. You cannot do that. Maybe half the time it works out that way, maybe something like that. But that is not something that works out every time. It's just in this particular case, the waters move from one side to the other, and what was H plus on one side becomes the same number of OH minuses on the other side. It does not always work out exactly that way. So don't try to take a shortcut. Actually do the process all the way through. Cancel stuff out. Don't just assume that you know what's going to happen. Work through the process, and you will arrive at the correct answer. All right, in the next video we're going to jump into electrochemical cells, voltaic cells, which is a fancy way of saying batteries. So we will pick up there next